Hi, welcome to lesson 3 of IB Physics at Edu Solutions Institute. So today's lesson will be focusing on representing forces. Representing forces could be in the form of diagrams or it could be in the form of calculations. So the first thing that we need to know at this level is what exactly is a force? Now, a force is any action that causes an object to change its shape, its size, its motion. Right? So these actions could be like you push something, you pull something, you twist something. Those are actions that result in motion being changed, meaning it speeds it up, it slows it down, causes it to stop, it causes it to vibrate, or change the size of it, gets it bigger, gets it smaller, or its shape changes from what it was to something else. Now, in representing forces, we normally draw diagrams. Now, the first type of diagrams that we look at are called free body diagrams. Right? Now, free body diagrams are essential sketches that shows us how the forces are acting on an object, where they originate from, as well as the direction that these forces are going. So example, if we look at a free body diagram of a book on a table. So this is my table here, and then I put a book on this table. The free body diagram now will give us which forces are acting on this book. For one, we know the book exerts a force from its center of mass downwards, and that force is called the weight. So that's originally one of the first forces we know. But because this force is pushing down on the table is exerting that same force back up on the book. So from the surface of your table up in that same line of action, we have this force called a normal force. Right? And from now on, the normal force will be represented by an R. The R, because the resultant force is our because of the result of this weight action that we get the normal force being active. So we notice one, the length of these two forces must be the same, right? Because this force is equal to this force. Now that's the two forces that's acting. Reason being the book is not moving, right? But let's say the book was moving. What will change? So it's still on the table, right? But this time, the book is being pushed. So the book on the surface of the table, and it's being pushed right here with an F force. Then, or same thing, our weight will act vertically downwards. We're going to call it W. And we also have our normal force still present, going upwards, R. Now, if this is not a frictionless material, then we will have your friction force. Now, your friction force would be opposing the motion, meaning it would be going in this direction. We can call that frictional force F subscript F. Now, we notice that this pushing force is greater than your frictional force because the book is being moved that way. So your frictional force cannot be longer than your pushing force. Now, also note that your diagram shows that the frictional force originates from the bottom of your book contact with the table, because that's where friction will be present. So it is important to draw it from the origin of the forces to the direction that the forces are going. Now let's examine an object falling in the air. So we have this object falling in the air. Now what do we know? We still know that there is a force from the center of the object going down, which is the weight. right? Now, if this object is speeding up, right, we're going to have air resistance acting on this object. Now, air resistance, we'll be putting it upwards, right? Let's call this air resistance. Right? Notice the air resistance size is smaller than your weight because the object is going down, right? So therefore, more force pushing it down than up. So these diagrams represent your free body diagrams, right? So these are diagrams that represent the forces that are acting on the object as well as the origin and direction of these forces. Now, final one for free body diagram is, and this one we'll use in the future, is objects on an incline. So let's say this object is sliding down an incline without anything pushing it down. We know that there is an origin, the weight vertically downwards, right? And then we have our frictional force, again, at the surface of your contact, your frictional force is there. Now, in future reference, the weight will be classified in two aspects, right? This here is your normal force. We can call that R, right? So normal is always 90 to the surface of your plane that is in contact. So just like this is 90 degrees normal. This is 90 degrees normal. This here is 90 degree normal to the surface. All right. So these are free body diagrams. Now, finally, for the second session of this lesson, we'll be looking at some calculation base. Because representing forces, we use arrows just like these to represent direction and size of force. But what if we wanted to know what's the net force of objects on of forces on an object? Now the net force or resultant force tells us after all these forces are acting, where is the final force going, or where is the object going to move towards. Now at IB level, they want us to focus on 2 or 3 forces acting at angles. So let's say we have a object here that is being pulled in this direction by a 10 Newton force, but it's being pulled at an angle to the horizontal of 30 degrees. And then it's being pulled in this direction by a 15 Newton force. So this one is on the horizontal, this one is at an angle to the horizontal. Now, just by looking at this, we know that if these two forces are pulling on this object, the object will move somewhere in between those two forces. Now, at this level, we will not speculate or guess where. We will calculate to give a definite answer of where exactly here the object will be going and what is that net force that it's moving with. So the first step in doing these calculations is to isolate the vectors that are acting on the object. Isolate them means we draw them as separate. So we have 1 Newton, the 15 Newton here, and we can call this F1. And this F1 is only in the X plane. So we're going to call this F1X, right? Because it's the first force and it's only in the X plane, horizontal. Then we take away the 10 Newton. It's acting 15 degrees, 30 degrees, sorry, to the horizontal. So in this case, we can call this F2 force. And notice because it has an angle, there is an X that is pushing it this way. We're going to call it F2X. And there is a Y pushing it up this way, which is called F2Y. So in this case, we have to know what these two values are. How do we know what this one is? This is adjacent to the angle. So that means we use that F2x is equal to the force F2 cos the angle theta. Right? And this is 10 cos 30 degrees. Right? So taking up my calculator, if we go with that, the 10 cos theta, please ensure that your calculator would be in degrees mode. If it's in radians, it will give you an incorrect answer. But in degrees mode, this gives us 8.66 newtons. And then we do the same for the y. So we go with F2y. Now this is opposite to the angle. So therefore it now becomes sine theta. And that's equal to 10 sine 30. And 10 sine 30 is 5 newtons. So now we know that there is a x going here, there is a y going here of these two values respectively. Now the final step is that we replace this angled vector with the x and the y vector. So here we can put back F1 being 50 newtons. We know that F2x is going that way, so we can say it's moving that way at 8.66 newtons, and then we know there's a y going up of 5 newtons. So what this now tells us is that because these two are going opposite direction, we're going to subtract them. So it's 15 minus 8.66, which gives us that we have a 6.34 newton going this way because it's in the larger force direction, and we still have just the y of 5 going up. So therefore we know that there is a resultant vector r in that direction. How do we find that r? It's always Pythagoras theorem. So it's the square root of 6.34 squared plus 5 squared. And that gives us an answer of 8.07, and we're using the smallest significant figure we started off with, which is 1, so that is 8 newtons. So what this tells us is that this box is moving at a net force of 8 newtons. Now we need to know what's the angle. We can find the angle to the horizontal, or we can find the angle to the vertical. So let's find it to the horizontal. So we're going to find theta. So theta, we can use tan. So it's the tan inverse of the opposite side, which if this side is 5, this side also is 5 newtons. So it's a 5 over the adjacent, which is 6.34. And that tells us that it is tan inverse of 5 over 6.34, which is 38 degrees. And what this means is that the resultant is acting here with a value of 8 newtons at an angle to the horizontal of 38 degrees. And that is how we will find the resultant force of any objects, of any force acting on an object with moving at different angles. So I'm going to post a question here, right? And I want you guys to attempt this and give me your final answer in the comment section below, right? And thank you for listening. Hope you learned something new today, and I'll see you next week. Bye bye.